Okay, I think we'll get going now. So welcome everyone. We're now deep into the final quarter of Groundswell 2022. I hope everyone's had a very stimulating and edifying time so far. In this session, we're going to be talking about improved nutrient management using zero carbon fertilizers. Now, this may not sound like the most glamorous of titles, but I believe that this is an incredibly exciting new direction, a symbiosis between industry and agriculture that can yield a multitude of benefits. And if you don't believe me, maybe you can believe others that you may trust. The Prince of Wales launched his Sustainable Markets Initiative a few years back, and along with that, a TV channel called Re-TV, and CCM Technology, who is the main subject of this session, were featured as one of the first films. And then Tom Heap, who also was presenting earlier in the day in the big tent, he named it CCM Technologies fertiliser pellets as one of the 39 technologies that can save the planet. So I think we're going to be in for a good session. But because I've been to Groundswell 3 times now, I'm conscious of information overload. There's so much to take in that sometimes you feel like your brain is just too full. There's no room in the brain hard drive. So if you can just take one thing away from this session, is this: the dominant economic model at the moment is that it's a waste-creating machine. But in a circular economy, waste can be reimagined as feedstock for nature-positive products and materials, exemplified by CCM Technologies' product. And shifting to a circular economy can reduce pressure on our resource-constrained planet, as well as addressing many global challenges, such as a climate emergency and pollution. So that's the key message for this session. My name is Nick Jeffries. I work at the Ellen MacArthur Foundation. We're a charity based on the NGO. Our whole thing is about accelerating the transition to a circular economy. I'm an environmental engineer by profession, and my role today is to set the context for CCM Technology, as well as ask Peter questions and take questions from you in the audience. So Peter, would you like to introduce yourself?
Yeah, hi, I'm Peter Hammond, and I am Chief Technology Officer at CCM Technologies and one of the founders of the business. My background for the last 20 years or so has been in process development within chemical engineering, particularly using carbon dioxide as a way of creating new materials and reducing the overall carbon impact that those materials produce on the environment. But before that, going sort of right back in my early career, I farmed in my own right down in Cornwall for about 8 years, producing what were the crops down there, which was early potatoes, daffodils, some specialist horticultural crops, and grass. I then moved on from that to work up in the Cotswolds on managing a larger enterprise which produced principally malting barley and sheep. After that, I moved into wider food processing, where on the more industrial side, looking at production of tomatoes and orange juice, not in the UK, but in West Coast of the United States and in South America. From there, that's really where my interest in processing came along from. And after that, I really changed over to the development of processing systems that delivered higher value from agricultural crops. And so that ended up taking me towards a whole range of things that are producing different sorts of phytochemicals, either for nutraceuticals or as actives in foods and that sort of thing, but also into wider food processing, into the pharma industry, and also into oil and gas as well. But using, throughout that time, carbon dioxide as a tool to generate change and produce clean products.
Excellent, thank you, Peter. Now we were hoping, even though Peter has a little bit of a farming background in his past, we were hoping to have a farmer on the stage today so they could offer their perspective, but that wasn't possible. But it's great. We have an audience, and how many farmers are there in the audience? Because hopefully we'll have a discussion later. So great. So at least we have a farmer perspective represented in the audience. So can I just set the context a little bit? So what CCM is doing fits into the framework of what I've just mentioned a few times is the circular economy. And I work for this organisation called the Ellen MacArthur Foundation. And I think most of you probably know Ellen MacArthur as a world record beating sailor. I think, was that fair to say? That's what she's best known for. So what was she doing setting up a foundation that promotes the circular economy? Well, as the story goes. So when she was doing her world record attempt, she was like in the Southern Ocean. The nearest person to her was actually on the International Space Station. And she had a lot of time to think about things. And one thing she really thought about was this idea of finite. Because what she had on her boat were a number of finite resources that she had to manage very effectively. She had to make best use of renewable resources, like the wind and the sun. And if she broke anything, she had to fix it. And when she got back to shore, she had a bit of an epiphany moment that life on a boat is actually quite similar to the global economy. Our global economy relies on the consumption of finite resources to thrive and to grow. And by definition, this is not possible. This will not last in the long term. And so she started her new journey, setting up the Ellen MacArthur Foundation. And what the circular economy, which is, as I say, whose whole raison d'etre is to promote and accelerate the transition to a circular economy. What do we mean by a circular economy? A circular economy is based on 3 principles: eliminating waste and pollution, keeping resources in use, and regenerating natural systems. So, in a way, the circular economy is more like it's like a natural system. Everything is connected. Waste from one part of the system is food in another part of the system, and the whole system regenerates and revitalizes itself. But we're pretty far away from that. So we've applied the circular economy model to all different parts of the economy: plastic packaging, fashion, and then in 2018, we started looking at food. And we did a very, very detailed analysis of the food system. And that analysis yielded some things that I think probably most of the people in this tent are aware of, that there is a huge environmental and social cost to the food system. But also, at every stage of the food value chain, there are losses. And then eventually you get to the end, and only 2% of organic waste is actually cycled back to productive use. But there are many companies who are seeing this as an opportunity, not as waste, but as feedstock. So if we just look at this slide here, on the left, this lady, she's modeling something that's made out of, it's leather. It's actually mushroom leather grown on waste corn stover. It's called Milo leather. It's a collaboration between Bolt Threads and Ecovative in the US. Toast ale, I'm sure many of you are familiar with. That was set up, 30% replacement of the malted grain is leftover bread. And then on the far right, that is a bag of insect feed that has been produced from just black soldier fly larvae feeding on organic waste coming out of cities. So there is a great opportunity in reimagining, looking at waste as actually, food for another part of the system. And it's greatly exemplified by CCM Technologies. One of the first bits of analysis that I saw when I joined the foundation 6-7 years ago is that actually in the discarded organic resources globally, there's 2.7 times the NPK that is used in chemical fertilizers. Yeah, of course, there are challenges in capturing that, but it just points to this amazing opportunity. So that's the context. Over to you, Peter. So tell us about CCM Technologies. Tell me about the what you're doing and the process.
Okay, so as has been highlighted there's a huge amount of resources available in the waste sector. The trick is actually getting those, gathering them together, and then creating stable formulations that are actually appropriate for their end use. So you don't want to use them in their raw state. Now, what we do is go to the point where the first sort of reconcentration, if you like, of those nutrients take place. So obviously they're grown on the farm, they go out into various food systems, and they end up coming back as waste one way or another. Now, it so happens that as part of the way that government policies try to produce more sustainable fuel, one of the things that feeds into that is the generation of biogas. And so there's been a network of facilities throughout the country that are starting to agglomerate a whole range of waste materials. So they're being fed into those sites, they're being digested. Some of the more available materials are made into biogas, and those are returned to the energy system. But what's left over is this sort of sludgy material, which is quite rich in nutrients, but is obviously dependent on what you put into it. But it is a good basic resource. So what we do is stabilize that material. And the first step in that stabilization is to deal with the nitrogen that's in that material, which is most commonly available, the most available and easily lost material is in the form of ammonia. And so our process targets that ammonia by adding carbon dioxide to the system. And that carbon dioxide is actually gathered from the combustion process that's used to generate electricity when the biogas that's produced on that site is actually generated in the first place. We use that CO2 to stabilize the ammonia, and then we carry it on, so it produces a bicarbonate material, and this is all happening in and around the organic matrix that is present in the digestates. And then we carry out the final stabilization step by converting those ammonium bicarbonates into either ammonium sulfate or ammonium nitrate, depending on which chemical route we choose to go with. And at the same time, we reprecipitate the carbon dioxide as chalk, calcium carbonate. So at the heart of our process, we've got this organic framework, if you like, with a high stabilized nitrogen content that's all bound together with chalk. Now, into that process, as the materials are being made, we can add either other waste nutrients. So if we wanted a higher K content, that sort of thing, we can add in wood ash and that sort of material to push it up, or other nutrients to produce particular formulations. But it's really what it's about is the stabilization of those nutrients at source, using that as a backbone for a formulation that is appropriate to what an agricultural, what the agricultural use will be at the end of the day.
Okay. So you just described a technology, a process, but that yields a product. But it's a technology. Sorry, it's a sort of almost like an agnostic process. It can be applied to all different sort of industrial contexts. Is that right?
Yeah, that's absolutely right. So the most obviously circular application for our technology is one of our first users in the potato industry, where we're taking waste peelings from a crisp manufacturing plant, taking that digestate and the CO2 that's produced on that site as well, and the nitrogen that's entrained in those materials, and producing a fertiliser that goes back into growing potatoes. But as you say, the process is agnostic to whatever the digestate is. So long as there's organic material in the mix and there is nitrogen in the form of ammonia and there's CO2 available, we can make our process work. Okay. Yeah.
And what you're left with is a pellet. Yeah.
Yeah. Well, we start off with a fibrous mess, and then that's actually dried using some of the heat that's available on the site from the combustion process that generates the electricity. So there's a minimal amount of energy brought onto the site. So the actual manufacturing process is very low energy. So that was the key starting point for us, because as I mentioned before, my background is really in process development. So it was looking at how we get to make a product using our process. And there, we come up with a way of using recycled materials, recovered energy, that allowed us to produce a nitrogen fertilizer, which we can talk about how that works later. But in comparison to the conventional methods for making nitrogen fertiliser, we have a situation where our product at the factory gate, if you like, we will use in the development of that fertiliser something like 300 kilos of CO2 will be developed, as in will it generate it. But that compares to the best conventional route at the moment, will be producing at least 3.5 tonnes of CO2, and the UK average is actually around 4.5 tonnes of CO2. So you've got a 90% reduction in the manufacturing stage in the production of CO2. So it's a significant impact at that point. But what's interesting is that that's really when we started out on this process 7 or 8 years ago, we thought that was it done. It was only when we were trialling the material as we're going forward that we've appreciated that the other components of the system, not just the NPK, the organic side was having a very substantial effect on the way the material actually worked in field.
Yeah. Okay. So you mentioned your trials of the material. Can you sort of describe that in a little bit more detail? So where are you in terms of how much volume you're producing? Yeah, where have you trialled it, and what are the results that you've seen?
So we've actually been making this material for the last 7 years now. We're in our 8th year of trials. We started off very much trying to show that we were making a fertiliser. So we put it into straight comparative trials, all the usual random plot trials against either ammonium nitrate or urea. And we found right from the outset that we were getting the same nitrogen response as you would expect from either ammonium nitrate or urea. We originally started out at first tests were at Cirencester and Harper on grass and cereals, and they continued there for about 3 years, and then we moved on to using Cranfield and Velcourt for most of the trials, mainly because we were concentrating on combinable crops, and it was easier to have more sites through the Velcourt system. And as I say, right from the outset, we were getting yield equivalents for nitrogen applied to the field. But over the last 3 years, we started to see that we were getting additional benefits. And these were initially highlighted some work that was done at the University of Sheffield, where they started to look at what the emissions were coming from the material. So we found out, compared to, particularly to urea, obviously, that the emissions to air were significantly lower. Perhaps more interestingly, the losses in terms of leaching of nitrogen from the system, both in urea and ammonium nitrate systems, were significantly lower. So we're losing about 70% less nitrogen from the system than you would expect from a conventional prill. And then on top of that, there is a sort of semi-slow release aspect of the fertiliser, where essentially about 80% of the N is released in the first 10 to 14 days, but the rest comes out over another 10 to 14 days, so that the material is around for longer. But the top and bottom of that is that we're basically losing less material from the system, and that has meant that we're able to apply less nutrient to the ground in the first place. And certainly we found for the last 2 years with the we've been using our Velcourt trials, we've just been applying 20% less nutrient, and we've been achieving the same yields as the conventional sort of recommended application of nitrogen. But more to the point, we're still getting the same transfer of nitrogen to protein quality in the wheat and oil quantities in the oil seeds as well. So there's useful things going on there.
Yeah. So that's a really, really big deal, because as I understand it, if you look at all the planetary boundaries, sort of the geophysical limits on our planet, the NNP into water bodies is the one that we're exceeding the greatest. But CCM pellets, there's much less issues with runoff from fields, and also it sort of it doesn't mineralise. Does it only get activated? Is it mineralised when the plants need it?
Oh yeah. The nitrogen cycle works the same as it always does. So we haven't done anything clever in that sense at all. The only thing that we're doing is that we're taking that nitrogen we're reducing the amount that's going off into the wider environment, but also, I said that we formulate particular, whatever formulation you want within reason you can have. But clearly, the levels of nitrogen are not always present in the digestates you get. So we're having to bring nitrogen into those systems. And what we're doing there is actually recovering the nitrogen from either wastewater systems and certainly the phosphorus as well. So we're actually helping to clean some of those streams up and put that nitrogen back into the fertiliser. So it's, there is a net reduction of free nitrogen in the system, if you like.
Does anyone have any questions about that? Because I'm conscious that I'm not a farmer, and so the farmers in the audience, you've heard what Peter said. What's your reaction to this? Over there, yeah.
Hi, I'm John Walsh I'm a vet and a farmer. If someone's got a digester on their farm, is it scalable at that level to put that on?
If you'd asked me that last year, I'd have said no, is what it comes down to. But we're very aware that there's a lot of that sort of 500 kilowatt type digesters around the farm. And the great thing for us is they produce a particularly nice sort of digestate. So what we've got now is a system where we can actually carry out the stabilisation step at that farm where the smaller digester is, and a level of drying, and then that material can be taken to a central hub, if you like, where it can be formulated with other things. And the great advantage of that is it allows us to access those sorts of material, but it also means that we can bring in a diverse range of digestates into a central area, so we can have a wider variety of formulations that we can make.
Other question?
Keith Truitt, agronomist. So my question was, on the BBC 59 Ways to Save the Planet, the Tom Heap programme, there was a similar technology, which I think might have been yours, but they were using the same sort of stuff to treat sewage from a sewage treatment.
Yeah, we can do sewage as well, yeah.
So that's a massive source of nutrients that's basically untapped. That if you could get into that source, that would be brilliant, wouldn't
it? We tend not to use the S word, to be honest, because it's sensitive in different ways for different people. There are underlying issues potentially around some of the nastier things in it, the heavy metals and heavy plastics. But when it comes down to it, those are actually at much lower levels than they were before, and I think those materials, a lot of them are being spread anyway. I think what our process does is allow those materials to be brought back, but in a monitored way. So all our stuff, we analyse it to Kingdom Come when it comes in to make sure it hasn't got any nasties in. And by and large, most of the domestic sewage these days is very low in what we would regard, everybody would regard as harmful materials. But for us, we see that that is a massive resource that will come online in a more, obviously it's there to a degree already, but will come in line in a more stabilised and refined form over the next 3-5 years. But there's quite rightly regulatory hurdles that have got to be gone over to allow that material to get back in the market. Having said that, whilst those issues are very reasonable around the sludge side of things, it does mean that we can access the ammonia that's held in the liquids, because we can extract that as a straight chemical without any issues around heavy metals or heavy organics. And likewise, already there's the products that are bringing the phosphate back in as well. So it's there. It is the massive untapped resource that we need to get to. But obviously we've got to be aware of the sensitivities and sensible about the any harmful impacts that it could have. But it's the big one to use,
Thank you, Debbie Gossman. I work with reducing ammonia emissions on farm. It's really good that you're talking about ammonia emissions, but I think you've only just touched the surface. Our ammonia emission levels have to come down so much by 2030 because of the health problems that we're all facing, particularly in this area regarding air pollution. And if anybody looks at the World Health Organization's latest figures, you'll see a very good map which shows what the problem is. And many of the emissions are coming from agriculture. And anaerobic digestion is one of the areas where we haven't been able to meet our targets because of the increase in ammonia emissions from anaerobic digestion. So so have you looked at the full cycle? Because actually we've probably got too much nitrogen in the system altogether, and we need to prevent the waste occurring in the first place. So that was really my question.
I agree with all those points. I think the key thing is, what we have failed to realise until relatively recently is how much ammonia is lost in the system. A lot of it is coming from, yes, it's coming from those digesters. It's coming from other agricultural products as well. Then obviously the easy one that comes to mind on that is the chicken production. But I think the key thing there is the quantity of that material that is available that we can now stabilise. Now, ours isn't the only technology that can do that. There are others. I think ours is relatively straightforward and can produce quite rapid results. But that's to some extent for others to determine. But from a chemical point of view, we can stabilise those materials. But we need to do so quickly because they're causing more damage than the CO2 is, quite frankly. And those are the things. And they by their very nature they permeate everywhere. So we've got to put a block on them going in the system. And I think one of the key things for us is that we've talked a lot about the conventional nutrients, the NPK side of things. I think probably, and this is where we as a company need help from the agricultural community, is that we're just starting to realise how much importance there is to the other half of our pellet, because we make a brown pellet thing, and about half of it is the NPK, the other half is all organic materials. Now, those all organic materials are having a considerable ameliorating effect on the way those nutrients work, and also I think in time, as those materials sort of are reintroduced into the soil and reintroduce balance in the soil, actually the requirement for total application of N will be reduced very significantly. So I think over a long period we can use less N, and that's something that we should all strive to do, I think.
Yeah, before we,
I'm Philip Dunn. I'm a farmer. I'm an MP. I chair the Environmental Audit Committee, and you and your company have given evidence to us in some of our inquiries. So thank you very much for that. I'm very encouraged by what you're doing. You started to touch on the regulatory requirement, and it'd be very helpful to understand the extent to which you're being helped or hindered by both Natural England and the Environment Agency in getting your technologies deployed on farms.
Okay, certainly it is the proverbial curate's egg on that. I think very much it's not so much Natural England, it's very much because of the way if we focus on the sewage industry to start off with, there is the operations, the regulations were put in force to ensure that the environment wasn't damaged by the materials being put back into it. Things have moved on in the, I think, 25 years since those regulations were initially put in force. But there are some anomalies in the way that system works. So, for example, whilst we have very good relations with the Environment Agency itself, and they've very much bought into what we're doing and they're very helpful, the structure by which those materials are released into the environment is released back out of the waste system, if you like, is still very much governed by the local officer who covers the permitting period, permitting regulations in that facility. Now, they can take advice from higher up, but I think, to be fair, there's a combination of it's a new technology to them. There is some reluctance of putting their neck on the block, which is also, I must admit, aided by the it's people are supposed to be my customers, but the water companies are not necessarily the fastest moving people in adoption of new technology. So they tend not to apply pressure where it would have get results from the Environment Agency. So at the moment, and again, it's because of the help that you were able to bring us that 6 months ago, we're getting there, but it's very much walking through treacle, unfortunately, and it is partly the Environment Agency, but actually it is partly the water industry as well. So that's that one. The water industry is the worst case. The others, we have got their get rounds on, and there is a process within the Environment Agency where we can achieve end of waste for a range of other products, and that is going better. Still not there yet, but we're going in the right direction. Thank you for it.
Okay, well, so you mentioned regulatory issues and some of the sort of slow-moving utility companies, but what other hurdles are there to overcome to really scale this up?
Yeah. Well, our biggest problem is that we can't make the stuff fast enough, to be honest. Our original business model was that we would sell the technology into large companies who had, the balance sheet to do it and the waste resources and all that sort of thing. That has worked to an extent, and we have a lot of interested people, but they do move very slowly. So, that has been a slight disappointment to us. And so what we've done in the last year is take the opportunity to actually, because of the way things have changed in the last year in terms of the fertiliser market, there's a lot of demand for product, and so we have taken the decision that we will actually build our own facilities, and we managed to put one together last year, the facility in Shropshire, which will be upgraded for next season, and another unit coming online later in the year. So the scale up is just starting, and the real thing that is determining that is the demand for the product. But the trouble is we can't build quick enough at the moment, is what it comes down to. So all the material that we're making now is essentially going to be making up the shortfall that should have been met by the larger plants that haven't been completed yet. So so there's not as much material to feed into the system as we would like.
Feedstock. Okay.
Yeah.
Is there a question at the back there? Yeah.
Yeah, so you've just started touching on, I'm a farmer, so what I really want to know is, can I buy it? If I can't buy it, when will I be able to buy it? How much will it cost? What's the analysis? How can I spread it?
That all. Okay, so
the spreading one's
fortunately, you're not the first farmer who's come up with those questions. So, in almost reverse order, we would expect significant volumes to be available from 2025 onwards. And what would be good is if I can give you my card or whatever afterwards, there will be some material available for discerning individuals such as yourself who might want to try the stuff next year. We can let you have some, so that'll be fine. But it won't. We can't sell you all your fertiliser next year. But hopefully from 2025 onwards, and then really it's going to be close to 2030 before we've got very significant impact on the wider market. Cost-wise, when we started out on this, the whole point is from the beginning, it's been a carbon reduction project. But it was based on the fact that we were doing the carbon reduction within the project, within the process, and what we needed to do was essentially access a commodity market at a sensible price, so it would offset the cost of production, if you like. So from the beginning, we've made sure that we were able to produce at or close to conventional nutrient price, and we can still do that. And obviously at the moment, things have, we can probably make it less expensively than conventional fertilizer. So by and large, that our pricing structure is quite simple, that you essentially pay the nutrient price, but what we get on top of that, which is something we haven't really touched on yet, is so you buy a nutrient price, we can just about make it pay at that level, but then the carbon that's entrained and saved by the product is split between the farmer and ourselves. Or between the end user. That's where it gets complicated, but yeah, in simple terms, that's that. How do you deliver it to the field? Well, we've carried out spreading trials right from the beginning, because obviously we know if you can't get the stuff down, that's no good. And we depending on how the materials are delivered. So we've got different sorts of pellet, if you like, but they can be delivered pneumatically. They can also be delivered in trench with single trench potato planting, that sort of thing. The most common method of delivery is with a conventional spinner, which you have to alter the settings on it, but basically you can spin it out the same way that you would do with conventional prills. Goes out easily to 30 metres. We've had trials that say it's fine out to 36, but I think, to be honest, that's pushing the luck on it. And also, you've got to bear in mind with this material, only half of it is nutrient. So you're actually putting an extra stuff on as well. So I think what we need to be looking at maybe is fewer applications, but from a bigger hopper. So certainly we've got people looking at this year where they're spreading to 24 metres, but they're doing it with essentially with a line spreader. That's what it comes down to. So they're putting out a massive amount of material, but it does the job. Is what it comes to. And so I think that's key for us, is looking at how we develop the agronomy specific to this product and products like it in the future. Because at the moment we're very much fitted into, well, this is how you do fertiliser application. So we followed suit so that we proved that we were like that. But actually now we're thinking, well, we need to move away from that model and apply it in a different way.
That's brilliant, thank you. So generally have a lower nitrogen content than we're used to.
Yeah.
You'd put a lot more on.
Yeah. But you in general you get about 20% less. So we normally, most of our product, we can do higher end, but normally we only do a 15N. So you're putting twice as much down and then only half of it. So you're putting a lot more material on the soil.
Thank you.
So I've been. Oh, sorry. Do you want to, okay. Well, maybe while the microphone goes up. So there's carbon is pretty well every single presentation that I've dialed into is discussed. This is a regenerative agriculture conference. Your pellets have a good carbon story. Not only global fertiliser production, not only is it about 1% of GHGs, but we're losing carbon from our soil, year on year. So can you just unpack the carbon story a little bit, and then we'll come to this gentleman over here.
So the carbon impact comes from us in two ways. So there's as I highlighted at the beginning, there's the process for manufacturing the material is significantly less intensive than conventional nitrogen production. So that's good. There's a big win on that side. But when it actually comes down to the pellet, there's two things really. One is the fact that you will be applying less nitrogen. So there are a range of systems. And in fact, interestingly, one of the guys who came round to our stand earlier today was a banking person, and they're interested in, with Rabobank, and they're looking at creating systems where reductions in nitrogen result in payments to the farmers. So those systems are in place. So part of it is an offset in relation to using less nitrogen. The rest and a product that has lower intensity of production. The other part is physically the carbon that we're putting back into the soil, and that comes in sort of two forms really. There's one, as I say, roughly half the pellet of a standard fertiliser system for us will be organic. Of that organic fraction, about 2/3 of it is sort of more stable carbon. So that's the stuff that's been munched away at already by bacteria. And so that has a sort of longer lifetime in the soil. And certainly with there's a range of standard assessments that you can run. The one we use is a European-based one, which is a thing called YARSO 7. And basically that tells you how much of that carbon will be left in the soil, assuming that it's carried out, assuming that there's conventional agricultural practice going on. Then they basically saying X amount of that carbon, which in our case is around 25%, will be left in the soil after a 30-year period. The other side of it is that the organic that's going in is a sort of the sort of more humic type material that's actually feeding that carbon cycle straight away. So you're not actually taking so much organic material out of the soil to make those nutrients work in the first place. So there's two bits going on.
So is that about 2 tons of your product is about, you say, half a ton or a ton will be there 30 years in the ground 30 years later?
About a third of a ton, but roughly speaking, you get every ton of, depending on the formulation and all that stuff, essentially every ton of fertiliser you put down creates a credit to the tune of 1 ton of CO2 saved. Now, there are formulations that go significantly higher than that, but the great thing about that's that's completely avoided. Currently, the sort of nitrogen equivalent of that would be costing you minus 4.5 tons of CO2. So there's actually a 5 ton gain. Yeah.
Sorry.
Yeah, hi Peter. Nick Humphreys, Chief Agronomist at N2 Applied.
Yeah.
Given that you're adding in organic carbon to the soil alongside this engineered product of NPK, you're getting the response and the versatility of a mineral nitrogen fertiliser or a mineral fertiliser. Are you still subject to organic spreading limitations because of that?
When you say terms
closed periods and
we have to put we have it just treated as an ordinary fertiliser at the moment. Yeah.
Yep.
So ironically, there is one exception to that in relation to some of the sewage spreading, where we have a site exemption. We can spread outside the window there, but normally it's the same regulations, which is something that would be ideal. We need to work on that one, but yeah, it's essentially the same. Yeah.
So okay, great, thanks.
Yeah.
Can I ask a quick question about the global south? So a lot of the growth in populations are going to be in the global south over the next 30 years. Is this, especially urban populations, more mouths to feed, more waste to deal with? Is this technology, do you think, applicable to that kind of context?
Yeah, I think it is, because it works on several levels. Because ultimately, we're dealing with the waste that is at the end of its life, if you like, and that is common to everywhere. Now, whether the sewage plants in those places work well or it's just left to rot so along, those nutrients are there and available, and they can be gathered in one form or another to feed into systems like the one we have. And certainly we've got a small scale unit that can be used to demonstrate that sort of thing in the south, and it will be going out. It's only going to southern Spain to start off with, but it will be crossing the Mediterranean, going south of that later on. So yeah, the technology, the waste is there in proportion to the number of people. Usually with a caveat surrounding that, but certainly there is sufficient materials there that you can genuinely create new fertilisers for those areas. I think the other thing we need to appreciate on those is, at the moment, these guys can't afford to buy the fertiliser. So, it's not like there's the competition there. It's actually making a new product available to them that will hopefully help in the stabilisation of their soils, but actually give them some increased yield as well, without having to spend usual amounts of money to access it. Because there's if they end up with a 5 or a 7N that they haven't had to do anything to, that's a major improvement on what they've had before. So, yeah.
And as we found that recently, things like fertilisers are prone to geopolitical shocks. And so if you have more regional fertiliser production, that gives you resilience as well?
Yeah, I think that it does. And I think that works on our model here, and this would work elsewhere. And this, we're looking at a much smaller zone of operation where we're gathering the resources in together to make a fertiliser product, and then distributing those again over we're not if we have a plant in Exeter, it will be producing materials to go into Somerset and Devon. It won't be sending them to Aberdeen. And that same sort of thing will help decentralise the manufacturing system, so that we won't be tied to production systems that are themselves tied to major sources of energy. So we will hopefully see a move away from production in the Middle East and in Russia and US, Canada. Yeah.
So, any more questions? I mean, in the front row here.
Hi. Just a quick question on the volume. If we've got 1 ton of ammonium nitrate, how many tons of your product do we need?
4 is the short answer. Yeah. But you get all those organic. Yeah.
So 4 times the storage.
4 times the storage problem, but 4 times the organic benefit in the soil. And also I think what we are seeing already, there's the reduction in primary use of the nutrient. We would expect that to fall considerably over time as you get the soil benefits right. But yeah, you're right. You have to put more on. Simple as that to start off with. Yeah.
A little question. How is your business structured?
as I say, so our model is that we develop the technology and we sell that technology to larger businesses. We will build the plants that have been built so far. We've overseen the construction of those units as well, and we will continue to operate that model. Our sort of principal customer at the moment, or two principal customers, are Severn Trent and PepsiCo through Walker's Crisps in Leicester. But we will now be building our own plants. And there, what we're interested in doing is we're finding new sites for those, but also accessing new sources of feedstock to feed into them. No, God, no, sorry. So the company has been. We're now about 30 people. We started about 7 years ago. No, sorry, we started longer ago than that. We've been doing the ag stuff for about 7 years. Originally, it's been angel funded until about 2 years ago. So we've had a very good group of angels who've been supported through that, and also a reasonable amount of grant funding. Then 2 years ago, we took in some investment from the outside from Whittington Finance, which is a finance arm for basically it's AB Foods and that sort of stuff. So they put some money in. And we will be going for more money to support our construction programme either the back end of this year or next year.
Okay. Oh, Mr. So is it John? Okay.
Philip.
Thank you. If you're allowing supplementaries, because we've got a little bit of time. You touched on, in answer to the question from the farmer at the back, I think, about pricing. Could you just clarify whether you're basing your pricing on the end value delivered in the product or some other calculation of nutrient?
No, it is that our price is at its simplest level. It's the NPK value in the product. That's what we base it on. There is usually NPK plus 5% as it's a compound. That's what we're doing at the moment. But we expect it to be based on that NPK as if you're buying them straight. That's what you should get from us. There is in the future there will be a splitting in one form or another of the carbon value that is attributed to the product, but that isn't fully decided yet, and yes, it's slightly complicated by the fact that there's a lot of people after that carbon. So it's who actually owns it. Is it the person who produced the digestate? And we tend to look at it that the carbon part of it will be split between whoever owns the digestate / product to start off with, and the N reduction that would produce on farm, that goes to the farmer. So there's a split between the two, which are they're more or less 50-50 depending on what the system is. But yeah, that sort of structure in the long run.
Do you see the money, the carbon value going back into the agricultural community?
Yeah, I think for the end side, I think it has to, because I think that's where the saving is being generated. Because I think that at a really basic level, what they're doing is saying, if you grew 10 tons of wheat last year and you did it with 220 units of nitrogen, actually you've produced your 10 tons of wheat again, but this time you've done it with 160. So actually that you've dropped that by 60 units. You haven't been used, haven't been made, haven't caused any issues in the environment. So you should get credit for not using that material. That is something that happens on farm, and that's where it should stay. That's what it comes down to. We would also say that we're helpful in that, so we'd like some too. But essentially, most of that bit stays on the farm. The organic one, I think, that's always going to be. It's going to end up paying toward the feedstock, and I think the organic part, the farmers are going to get the benefit for it, but not necessarily the money. That seems to me the way it's looking at the moment, although that may well change. Oh yeah, undoubtedly. Yeah.
And we already spread it on our fields.
Exactly. Yeah.
And we have a heavy metal burden that we're not compensating.
Yeah. Yeah.
I mean, the plastics is something we're going to take up with 7
Yeah.
But,
yeah. So, yeah, I agree. The thing is to be able to make sure that the sewage can be used as a proper resource safely, is what it comes down to. And I think the point there, I think as far as we're concerned, we believe we've got the monitoring systems to make sure that we keep all the metals below the threshold levels and also the heavy organics as well. I think the plastics one, it'd be interesting to see how that plays out in the long run. But certainly what we've looked at is the worst case scenario for that will be that they end up having to remove that plastic through some sort of gasification process, so it's taken out that way. And what we are able to do is use the products of that gasification process, which for all intents and purposes are sort of ashy biochar, really. We can actually make products using that. So if that happens, we can go that way. And I think that's certainly with a lot of the sort of Dutch, German, Swiss have already done it. I think that may well happen with those sorts of materials. But as far as our process is concerned, we can use those as well. But it's the NPK bit that is where the value comes from in the short term. Thanks.
Peter, you've done a lot of talking, and so I'm going to close up now. I'm going to close with the story, actually. But before I do you have any last parting words to the regenerative agriculture community?
Yeah, I think that the main thing to me that has I think that there is an opportunity to really change the way things are done, but not one that necessitates a total step backwards in the way things are done. I think you can undoubtedly take the best of what's been achieved before, but I think there are, through the technologies that are available, ways that you can make agriculture not only sustainable, but go that step further and make it properly regenerative, and in the appropriate circumstances, keep the yields up to the appropriate levels. And so I think that is something that is achievable, and it's achievable with the sort of technologies that are available now. And I think it's incredibly important that you do that, because I think it's underestimated. Yeah, there's a lot. Everybody knows you can hang a lot of environmental burdens on agriculture, but it does, because of its reach and the acreages it farms over and the number of people it's got, it has got more capability to fix the climate crisis than any other industry in any industry in the world. So, it's keep it going and keep it developing is what it comes down to as far as I'm concerned. Thank you.
Amen to that. Okay, I just want to finish with just a little story that I came across in, I don't know if anyone's read The Third Plate by Dan Barber, and also David Montgomery's Dirt, The Erosion of Civilizations. And what he did, both of them authors did, is they compared the sewage management systems, or the waste management systems of the ancient Chinese Empire and the ancient Roman Empire. And actually there was a guy called Frederick King. He was an agronomist with the US Department of Agriculture. He went out to Asia for a 3-month study tour in I think it was 1905, looking at agriculture and waste management in Japan, Korea, and China, and how they managed to keep their soils fertile for so long, and there was a very, very much denser population in Asia than Europe, and basically, and this is the reason why, because the food came into cities, and then it was passed through the alimentary systems of humans. It was collected and then taken back to the rural areas, and that's how fertility was maintained. Whereas the Roman system, they had these Roman sewers, and essentially that was a great at obviously protecting public health, but that was a stripping of nutrients from the Mediterranean basin into the Mediterranean. And the evidence of the soil loss can be seen on the archaeology of the buildings. You can see the soil levels gone down, and eventually they had to shift their food production into North Africa. And so I just thought, maybe a little bit of an apocryphal story, but I thought it was a brilliant sort of illustration of linear versus circular nutrient management. Thank you very much, everyone. I hope you enjoyed this session. Enjoy the rest of your time here, and thank you.